Hello all, welcome back to this video on branch and bound application to 01 knapsack problem. So in this video we will explore a well-known NP hard problem, that is application of branch and bound to 01 knapsack using least cost strategy. Okay. So we'll solve 01 knapsack problem using branch and bound and also using least cost branch and bound method with specific least cost branch and bound method. So what exactly is 01 knapsack problem? We are given a collection of items, each with its own weight and value, and a knapsack with a limited weight capacity. The goal is to select a subset of items that maximizes the total value without exceeding the knapsack capacity. But here the twist is we can either include an item entirely or not at all include it. So here fractions are not allowed, no splitting. That's why it's called 01 knapsack problem. So diving deeper, we will be given a collection of items, each owning its weight and each with its own weight and value, and a knapsack with limited weight capacity. Okay, what is our goal? Goal is to select subset of items that maximize the total value without exceeding the knapsack capacity. Okay, this we already know because we have already discussed this in knapsack algorithm also. Okay, this is available, these details would be available in our knapsack algorithm video, and these are the prerequisites to understand the branch and bound methodology, least cost branch and bound methodology for 01 knapsack algorithm. So as these are the prerequisites, we are looking into it once again. Okay, so what is our goal? The goal is to select a subset of items to maximize the total value without exceeding the knapsack capacity. Each item can either be included or excluded, hence the name 01 knapsack. No fractions allowed. Okay, so there is a twist here because there is no splitting. This is a twist. No splitting allowed. Okay, so why can't we try all the combinations? Means why can't we try brute force algorithm? Why not brute force? Because this is 01 knapsack is a NP hard problem. What is NP hard? Non-deterministic polynomial time complexity problem. Okay, so that's why as it is an NP hard problem, we cannot go ahead with brute force checking all subsets because it is impractical for the large sets of data. Okay, so brute force is ruled out. impossible for large data sets. Okay. So branch and bound helps prune unpromising subsets. Pruning is skipping unpromising subsets early using bounds on maximum possible values. So first, in the earlier stages only, for example, this is my root node and this is my node 1 and node 2, node 3, and these are my children's, child 1, child 2, child 3. So for example, in this branch and bound algorithm, if I am calculating the calculating for 0, 1 knapsack problem, if I calculate my bound for this first node, if it is much greater than what we expect, then we'll select this. If it is less than what we expect or what we set as our margin, that is capacity, what we called as knapsack capacity, then we'll prune it, that is skip it. If this node is okay and if it reaches to the capacity of the knapsack, then we will go through the child also. If it is reaching, if we see that this node is reaching the capacity, then we'll go to the child nodes, or else we will prune it. Pruning means skipping it. Okay, I hope you just got the overview of what is going on, and we'll discuss in deeper in the next examples. So how the LC, least cost branch and bound, works for 0, 1 knapsack. We start by constructing a state space tree. The tree is called, in LC branch and bound, the tree is called state space tree. Okay, where each node represents a decision about including or excluding an item. As we have already seen, will include or exclude an item. Okay, including is 1 and excluding is 0. Each level corresponds to a decision on one item. So each level corresponds to decision on one item, whether to go ahead or not. Bounding. We calculate an upper bound for each node. As we have already said that we will calculate an upper bound for each node. Okay. The best possible value we could achieve from this point onward. So we'll calculate the best possible value we can achieve from this point onwards. Okay, from this point onwards. Okay. For example, if my capacity is 100 and from this first node itself, the best possible value I can achieve is 100, then I'll go ahead with this node. For the second node, if the best possible value we can achieve from the node 2 is only 50 and my knapsack capacity is 100, then I will prune it, simply prune it, because no use of going to the child and calculating it. I can save the time. Okay, the bound help us estimate the potential of the each path. What does our bound say? Bound helps us to estimate the potential of each path. Okay, so in the state space tree, I already have a knapsack capacity, and for the each node I will calculate the bound, that is upper bound, that is best possible value we can achieve from this part of the point, that is partial path. or a partial solution, you can say, we calculate the best possible value we can achieve from this point onwards. If it is 100, that is our maximum capacity, then we'll go ahead with it. If it is not reaching or it is not up to the mark of the capacity of the knapsack, we'll just prune it and will not go until towards our child node. Okay, this is our time. So least cost search, we maintain a priority queue of active nodes sorted by their bound values. So what is least cost search? It maintains a priority queue. Okay, priority queue with active nodes sorted by their bound values. Here the nodes are sorted based on their bound values in the decreasing order. Okay, so that the best bound value node stays on the top always. Best bound node always on top. Okay, so that it can be picked easily. So if we want to include or exclude the node, it is integrated into priority queue. But what happens is the nodes are sorted on bound values. Okay, obviously the excluding nodes will go to the bottom of the queue, but the nodes with higher value and with optimal solution always stays on the top of the priority queue. Whatever it might be, including or exclusion, we store it in the queue. Okay, next, pruning. If the node bound value is lower than the best solution, we prune it. Okay, if the node bound value is less than the current best solution, we'll prune it, discard it, and don't explore further childs. Okay. So what is updating the best solution? Every time we reach a complete solution, what is complete solution? That is from the root to the node to the child is the complete solution, that is a leaf node. We check if its value beats our current best. So this leaf value or leaf node beats our best current value, that is at least it is up to 100 of the capacity, it reaches the capacity, we will update the solution. For example, in this case, we have imagined that in the first path itself it is reaching up to 100. Then the leaf node is reaching the capacity. So we will update it as best solution. I hope it is clear till now. So nothing much in the algorithm. The same is explained in the code wise. So, what are the key points? The accuracy of the bound calculation plays a crucial role in the efficiency of the algorithm. So, how the algorithm turns out to be efficient is the accuracy of the bound calculation is important. Accuracy of bound calculation is important. Okay. By always expanding the most promising node first, this best first approach avoids wasting time on poor branches. So, by always expanding the most promising or the best first approach avoids wasting time on poor branches. So that's why we have a concept of least cost or priority queue. Okay, which always keeps the things sorted in a descending order so that maximum leaf node always stays at the first position. Okay, so compared to exhaustive search like brute force algorithm, it significantly, this algorithm, that is least cost branch and bound algorithm, reduces the number of nodes we all need to explore, reduces the number of nodes we need to explore. Okay, I hope everything is clear. Thank you.